All right, cool. I think we left off here at parsing expression last time. Okay, so personally, I think that parsing expression is the most interesting part of writing a parser. As we just saw, a parsing statement is relatively straightforward. We process token from left to right, expect or reject the next token, and if everything fits, we return an AST node. Parsing expressions, on the other hand, contains a few more challenges. Operator precedence is the first one that comes to mind and is best illustrated with an example. Let's say we want to parse the following arithmetic expression. Okay, what we want is an AST that represents the expression like this. That is to say, 5 multiplied by 5 needs to be deeper in the AST and evaluated earlier than the addition. In order to produce an AST that looks like this, the parser has to know about operator precedences, where the precedence is the multiplication is higher than the plus sign. That's the most common example for operator precedence. But there are a lot more cases where it's important. Consider this expression. Put together 5 plus 10 expression and give them a precedence bump. That which makes it easy to determine what the rest of the statement is supposed to be. Now look at this expression. Here, the minus operator appears at the beginning of the expression as a prefix operator, then as an infix operator in the middle. A variation of the same challenge appears here. Even though you might not recognize the parentheses as operator yet, they pose the same problem to us as the minus in the previous example. The outer pair of parentheses in this example denotes a group expression. The inner pair denotes a call expression. The validity of the token position now depends on the context. The tokens that come before and after and their precedence. So pretty much it seems like, okay, we need to determine what to put on the call stack first. So we need to put this first, and then we at the plus 10, and then the multiplication by 5. I think that's part of the challenge, and it seems like that's how the precedence is how you are going to be able to determine that. All right. In the monkey programming language, everything besides let and return statement is an expression. Okay, so let's include function as well then. So pretty much everything besides let and return statement is an expression. So what are the expression? Call expressions. Arithmetic. Infix operator, arithmetic operator. Call expression. Identifier is not expression 2. Okay. In his paper, Top-Down Operator Precedence, Pratt presents an approach to parsing expression that, in his own word, is very simple to understand, trivial to implement, easy to use, extremely efficient in practice, if not in theory, yet flexible enough to meet most reasonable syntactic need of users. The paper was published in 1973, but in many years since the idea presented by Pratt didn't gain a huge following. Only in recent years, other programmers rediscovered Pratt's paper, wrote about it, and caused Pratt's approach to parsing to rise in popularity. There's Douglas Crockford of the JavaScript The Good Parts fame article called Top-Down Operator Precedence that shows how to translate Pratt's idea to JavaScript. Okay. Prefix operator, postfix operator, infix operator. It's fine. Binary expression. The result of this expression is 55, not 100. That's because the multiplication operator has high precedence or high rank. It's fine. Infix. So prefix, postfix, infix, and precedence. Preparing the AST. The first thing we need to do for expression parsing is to prepare our AST. As we saw before, a program in Monkey It's a series of statements. Some are let statement, other return statement. We need to add a third type of statement to our AST, which is a expression statement. But an expression statement is not really a distinct statement. It's a statement that consists of solely of one expression. It's only a wrapper. We need it because it's totally legal in Monkey to write the following code. Okay. Alright, expression. Statement type. Yes, talking not little. Missing something? No. Alright. The AXT expression type has two field: token field, which every node has, and the expression field, which holds the expression. The AST expression statement fulfills the AST statement interface, which means we can add it to the statement slice of the AST program. That's what we add. Okay, that makes sense. A string method to our AST nodes. Okay. String. Now everything has to actually implement it. Program string bytes buffer as statements string as not string return items. Okay. Buffer minus string. Let's token little. That's fine. If ls value outright string times outright string outright string parse token literal. Return yes expression. Okay. I'm going to write the test case for it. AST test.go. Token type token ident literal ivar value ivar trf program.string wrong on q program.string. All right, so this test is just literally just testing out the printing. So we have pretty much a list statement. It's just a let statement. Has token of, yeah, it has let, it has identifier, and another identifier. Okay, so okay, yeah, makes sense to me. Time to write the pred parser. The pred parser main idea is the association of parsing functions, which pred calls semantic code with token types. Whenever this token is encountered, the parsing functions are called to parse the appropriate expression and return an AST node that represent it. Each token type can have two parsing functions associated with it, depending on whether the token is found in a prefix or an infix position. The first thing we need to do to set up these associations, we define the two type of function, a prefix parsing and an infix parsing function. Type prefix parse fn func ast expression infix parse fn ast expression. Okay. Prefix parse fn, so it's a map of token type prefix parse fn infix func p parser register prefix token type token type fn prefix parse fn p dot prefix parse fn token type fn. So you have to register this one by one. Just check the type. If now it's just checking the type, the expression type to be an identifier, which makes sense because food bar is an identifier. Ident.value not equal to foobar t not error f. Ident.value not as got as foobar and ident.value. Alright, that's a lot of lines. That's a lot of lines, but it's mostly just grunt work. We parse our input foobar, check the parser for error, make an assertion about the number of statement in the AST programming node, and then check that the only statement in programming statement is an AST expression statement. Then we check the AST expression statement expression that it is an AST identifier. I mean, it makes sense. Simple enough. So I'm expecting to have an error. Same error. Cool. We can go a little bit more. That's fine. Parser.go. Parse statement. Func p. Parser. Parse statement. So remember, the statement is let, return, and expression. Okay. p.cur token type type case token let What? What's going on? Key parsing. Default. What is going on? Okay, I'm gonna have to look into this. Because it seems like every time I just press enter and just tab, it just goes to somewhere else. Return P, parse expression, parse expression, parse return, return. Func P parser parse expression statement ast dot expression statement ast dot expression statement token p cur token statement expression equal p dot parse expression lowest. Where's lowest coming from? Okay, we need to add that. Seems like if p dot p token is token dot semicolon p dot next token return statement. All right, so we're building, so it's similar to the other parsing statements. So p, we need the parse expression. Okay, constant lowest equals equals plus greater sum product prefix call p parser parse expression custom. So there's a expression statement, and now we're parsing the expression. Prefix p dot prefix parse fn p dot cur token type. If prefix nil, return nil. If prefix is nil. Okay, left. Do we need to register the prefix function? Do we need to do that? Yeah, we do. Return left exp. That's the first version. All it does is checking whether we have a parsing associated with the p token type in the prefix position. If we do, it calls this parsing function. If not, it returns nil, which it does at the moment, since we haven't associated any tokens with any parsing functions yet. Okay, new. So, alright. P prefix parse fn equal make map token type prefix p dot register token. Parse. P.parse. Parse statement. Oh. Oh yeah, we already have this. Alright, whatever. It's fine. We modified a new function to initialize the prefix parse. But register the parsing function if you encounter a token type or token ident. Okay. Sorry, it passes. All right, this seems like a good stopping point.